Hello everyone and welcome once again to the second lecture of the second hour of the last lecture. Uh, as you know, in the previous hour we have derived the simulation in the MATLAB Simulink environment, but the version that I'm going to derive in this video is based on an M file. So you can create here a new script. For the sake of completeness, I have opened another folder called coded simulation in the previous folder, and I'm going to try to save everything here. So we can close this and we can close the files that were already open in the previous simulation. So I think here we can move on. I'm going to close everything, clear everything, and clear the screen. So let us recall, these simulations are running in discrete time steps in a continuous manner. So for this I need to define the time step as dt to be 0.001 or 0.0001, doesn't matter. So I have to define some value for the discrete period of the simulation. So at every 1 millisecond this simulation is going to be running. Now in order to create the loop, in order to create the things going on, in order to push the things going on, I can write here that for t from 0 value by increments of dt to end time, and I can define end time here to be 10 seconds, right? So this is, let me comment, sampling period of the simulation, that is the length of the simulation, and I can move on further. So length of the simulation time, and now we can continue with our, just a second, with our analysis. So our simulation will be running here inside this for loop at increments of dt. Of course, we have to create every simple block from scratch. So for this we have to define a lot of variables. I think I can define here the position of the system, the velocity of the system, and the acceleration of the system as the initial values being equal to 0. The moment you want to change the initial value, you just have to change the variable here, just we have done in the previous simulation inside the integrator block. Now, moving on further, we have okay, let me see, position, velocity, and accelerations are defined nicely. So let us move on. Here I think I can write here positions, velocities, accelerations. Yeah, the nominal mass, let's take it to be same with the previous one. The nominal torque constant, let's take it to be 1.8, the same with the previous one. And now we need an integrator structure. If you go back to the previous lecture notes, I already defined the integrator for you in discrete time. And in those derivations, I was referring to discretization method of the backward Euler. And there we had output over input to be defined as S. So the term S in continuous time was represented with z minus 1 over zt in discrete time. And that would give us 1 over t times uk minus 1. So if we invert this simply. We have already made the derivation for that, but I would like to do it once more. Okay, so if you try to represent S with Z minus 1 over ZT, or 1 minus Z2 minus 1 over T, if you divide everything by Z, so if this was equal to S, then we can claim that 1 over S, that's the integrator, is nothing but T over 1 minus Z2 minus 1, right? Which is equal to Y of Z over U of Z. And if you make cross multiplication, you can write here that U of Z times T is equal to Y of Z times 1 minus Y of Z times Z2 minus 1. So if we move from here to the coding implementation, we can claim that UK times time sample T, that T is actually DT, right, is equal to YK minus, if you look at this, it is YK minus 1, right? Because Z2 minus 1 was just waiting one step for the next result. And here it's easy to claim that your output YK is nothing but the previous response plus new input times the sampling time. So this is simply integration. The new response is equal to the previous response plus input times the sampling time. Okay, so let us try to keep them. Let us try to implement this in our function. So maybe we can write here an integrator function. So let us create a new function. Function output is YK, right? And the input, the function name is integrate, that takes UK YK minus 1. So let me call this Y old, Y new, and of course DT. Okay, so Y new is equal to Y old plus UK times, actually UK can also be called as U new input, U new times DT. Okay, this is our integrate function. You can write this as a function, or you can simply use this directly in the system. I think rather than writing the function, using directly inside would be much easier. So you can copy and paste it here. Of course, for example, here instead of Y new and U new could be called the acceleration response of your system, right? And Y old will be velocity response, Y new will be velocity response again. So old response plus acceleration times dt will be called the new response. Here you can write position response is equal to position response plus velocity response times dt again. So we're simply trying to implement these two integrators here. One from acceleration to velocity, the other from velocity to position. Okay. And Acceleration response. So go back to your simulation. Here the acceleration response of the system was just division by 1 over mn of tau input, right? So torque, let me call this, I'm going to call all of the torques as forces, or I can call them torques, TRQ, torque input will be defined here, and then the acceleration response will be defined as input torque over mn. So torque input over mass nominal, right? Now it's exactly at this point that we have to define everything, because torque input will be this term, torque input will be containing all of the input that's from the reference torque and the disturbances. So reference torque will be Iref Kn. Let's write them. Torque reference is equal to Iref times mass nominal. And torque input, this one is torque reference minus, so this is the reference torque minus all of the disturbance torques. What are these? They are F external from this, and then A cosine U minus A times cosine. Of course, our U here is nothing but position response of the system. We should call this position response. Actually, okay, response is all right. Response is okay. A times cosine position response, and then B times velocity response, again from the minus channel. So minus B times velocity response. There is another way. You can simply put a parenthesis here and close the parenthesis and change these to plus signs, just like what we did here. Plus, 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 everything is added up and it's subtracted from the reference torque. So you have the reference torque minus the disturbance torque equals to input torque. So torque input is torque reference minus all of the disturbances. Of course, if you're writing here A and B, you have to define those values, A, B. And I'm going to take them to be the same with the previous parameters function, like this. Okay, you have A, B, and F external all defined. That's exactly the same with the previous function. All right, so far so good. Now this is actually from this point down, it's our plant. We can call this plant. Okay. I think we can put one more and one more. All right, we have the plant here. Now, plant is, if you go back to this structure, plant is nothing but from the input torque to the responses, this part, with all of the disturbances acting in. So, from the input torque to position response. This was the plant. Now, I would like to implement the disturbance observer structure, DOB. Okay, how can we do this? how can we implement the disturbance observer? If you remember, if you go back, the disturbance observer is nothing but the reference current times Kn and velocity response times mng taken over G over S plus G low pass filter. So if we create a variable here, if we call this variable to be some dummy variable, that is Kn plus mng, sorry, Kn Iref, that is I'm sorry, this should be Iref times Kn. Okay, and it's called torque ref, right? Torque ref. Actually, I can erase this. No need to complicate the life, and write here Kn times Iref. So K nominal times Iref. This is our input torque, right? This part. Minus mng times q dot. Minus m nominal g times q dot was just the velocity response of your system. Don't forget to define g directly here to be, let's say, 2500. Okay. So input torque minus the response from your system. So this should go through a low pass filter, right? Now that part is a little bit tricky. We're going to try to implement this, and maybe we can save this as the coded simulation. I will be calling this as the dummy variable. Dummy 1 is this. Now what I need to do is to filter the dummy variable, but I'll call this dummy new. What I need to do is to filter the dummy variable, G over S plus G. Now, how can we implement the low pass filter in the simulation environment? So, if you remember, I also derived this in the previous classes. Let us go and have a look. First order low pass filter. So it's G over S plus G here, right? And its discrete implementation, if you use that discretization, backward-Euler discretization, was something like that. And if you look at its coding, it's nothing but that. 1 over GT plus 1, previous output plus GT UK. So I can write here that dummy filtered is nothing but 1 over, that is 1 over G times dt, right? 1 over GT plus 1 times YK minus 1 plus GT UK. So this is YK minus 1. That's the dummy old, because this is the previous output. I can actually call this filtered filtered response, and or new response. I can call this new response. New response, old response. But response doesn't look like a good name. New filtered response, old filtered response. Okay, now it looks nice. Let's go back. The new filtered response is nothing but 1 over GT plus 1 times the old filtered response plus G times T times UK. So plus G times dt times UK. UK is nothing but dummy new. Alright. Now, if you're writing such a function, if you're writing such iteration, you should first define the old filtered response to be equal to 0, and you shouldn't forget to add here that old filtered response is nothing but new filtered response to be used in the next iteration, because your algorithm is executing from top to bottom. So here old filtered response was in the memory and dummy new was calculated here, and then new filtered response comes. Maybe in order to save some variables, as you could all follow this, I will change that to this. I'll directly insert that inside and erase this part. Okay, new filtered response is 1 over gt plus 1 times. So let's look. New filtered response is 1 over gt plus 1 times old filtered response plus gt times input. Old filtered response plus gt times, so our input is here, kniref minus mng velocity response, and it's here. kniref, is it minus? No, it's plus, so we should change the sign. It should be plus. Okay, now we corrected our result. So that's the new filtered response, and you shouldn't forget to assign the new value to be the old value at the end of your simulation so that it can be used again. Let's go back to the system here, and we have velocity times mng being subtracted from this, which will give us the disturbance torque. Okay, torque disturbance is actually equal to new filtered response minus, so that's the new filtered response minus mng times the velocity. This is actually mng velocity response. Okay, so just these two lines are creating the disturbance observer for me. And I think I can write here that this disturbance current, which is here, is nothing but division of disturbance torque by Kn. It's torque disturbance over Kn. So far so good, right? Okay, we have implemented the disturbance observer. Now, if you go back, what we should do is to write here that Iref is nothing but the disturbance current plus the desired current, right? Maybe we can write it here. Iref is actually equal to I this from the previous section plus I desired. Now I desired is not defined here, right? In the controller section we're gonna define it. Okay, we have the controller section now. Now we can define it. Let's have a look at our reference. Reference was 1 sine 1t, right? So velocity reference is sine 1t, right? And acceleration reference is nothing but cosine 1 times t. Okay, now how can I create the desired current for my system? It's very simple, that the desired current, actually I have to move the controller to top somewhere here. So I desired is, if you look at this, I desired is acceleration desired times mn over kn. Acceleration desired times m nominal over k nominal, right? And what's acceleration desired? Acceleration, oops, sorry. Acceleration desired is what you find from the controller actually, right? We have derived so many controllers until now. The force controller, bilateral controller, grasping controller, position, velocity controller, many different controllers. And the desired acceleration should be generated making use of these controllers. So in our case, it's nothing but a velocity controller that is kv times the velocity error, kv times, it's actually what we have derived in the previous lecture, kv times velocity reference minus velocity response plus acceleration reference, right? Okay, so in the controller you have the desired acceleration, that is a scalar times the reference minus response velocities. So it's like this, kv times reference minus response, right? If we remove those connections, okay, kv times reference minus response plus feed forward term, that's the desired acceleration. I'm sorry, that's the reference acceleration, acceleration reference, right? Now, I desired is this desired acceleration times mn over kn, and with I desired and with the computed disturbance current from the previous loop, because don't forget that the disturbance once acts on the system and is being computed for the next iteration, then we can run our plant here. So we haven't defined yet that kv, let's write it here, kv is equal to some values, and this will bring us to the end of our simulation. But before we go on, we can write here, we can define the scopes. Scope 0, 0 is, okay, if you have a simulation that runs with dt time steps to this, in this range, you have to create scopes of equal magnitude. So we have already defined dt, maybe we can write it this way. So we will create an empty array of zeros whose length is the length of our simulation, and which is one column in dimension. So if you just have a look at this, for our system we have dt 0.001 and end time being equal to 10 seconds, you have 10,000 plus 1. The moment you change dt and the moment you change the simulation time, you're gonna have correspondingly proper scopes. So I'm going to create several scopes here. Scope 1, 2, 3, 4, 5, 6, 7, 8. You can create up to 9, which makes 10 scopes. What I usually do is to write here t, okay? So I'm going to write that, okay, before we move on, don't forget that this simulation runs in increments of dt, but these scopes are arrays which have indices being equal to integer values. In order to catch up with those values, you have to run inside another integer for recording the value. So we can call index being equal to 1, that's the index for scopes, and you can write here that index is equal to index plus 1, and before those you can write the scope 0 0. I usually assign scope 0 0 to be the time, so t. Okay, and similarly scope 0 1 2 3 4 5 6 7 8 9. Okay, the first scope records the time. Actually, the zeroth scope records the time. I think we can move on in order. So I'm going to write here position response, velocity response, acceleration response, velocity reference, acceleration reference, right? And you can actually include whatever variable you're interested in. For example, if you would like to estimate, if you'd like to observe the disturbance torque acting on the system, you can assign disturbance torque to some variables, and the rest you can simply comment out, close. Okay, so that's the indexed variable. So index is starting from 1, right? The first variable in first iteration, and as iterations go on, this index updates itself. Second is time t in the second step, and position response in the second step, velocity response in the second step, and so on and so forth. So with these you can simply close your simulation. From here to here I have the coding implementation of what we had in MATLAB Simulink environment, except one detail, that we would like to have some plots, right? Let's try to run this simulation. I think we can segment this recording simulation variables. Okay. Alright, recording simulation variables, and these are just updates. Alright, so let us first run this and see if we have some error. It's giving some error. Undefined functional variable velocity response. Alright, we have defined these, but we have to write here that they are response actually, right? Now let's run it once more. There is one more error. Undefined functional variable I disturbance current is also not defined. This is 0 at the beginning. I desired is 0 at the beginning, right? Iref is 0 at the beginning. Let's run this. Okay, as it runs, you can see all of these variables on the right hand side, which means that our simulation runs, but if it's correct or not, we can only observe if we look at the responses. Now, for easier plotting, you can simply write here figure hold. I'm usually using these hold on, grid on, and box on. These are actually holding the current graph on the figure so that you can plot multiple responses on the same figure. It's putting a grid, and it's showing the outer box of the grid screen. so that it looks fancier, it looks nicer. And here you can have plot. First, on the x-axis we have the time, which is scope 0, 0, comma. I would like to see velocity reference minus velocity reference versus velocity response. So scope 0, 4, 0, 4, that is, sorry, 0, 4. Scope 4 was velocity reference, right? With color red and with a line width of 2. And I would like to also see time versus velocity response, which is scope 02, with a black curve on the same plot. Let us see the results. Okay. Hopefully you can see the responses. Okay, here is it. Now, it's not it's not as good as we are desiring, but if we simply go up and change this dt to 0.0001, that is 10,000 iterations in 1 second, and if you run your simulation thereafter, you can see that those two plots are one on top of each other. Actually, we can change the colors. We can make this black and we can make this red with a dashed line. Okay, it's now easy to observe that reference and response are on top of one another. So this way of simulating a system is at the beginning not as intuitive as the previous one, because here you have all of the blocks, you can observe what's going on here, but in coding environment you have just few lines of codes, right? But if you once succeed in that, if you get used to that structure, it's much easier, much faster, because with one click you can directly get the response and you can play with any parameter you want here. For example, velocity convergence can be 0.05, which will give you a weakened response. And for example, the initial velocity could be, let's have a look at the block. Okay, initial velocity could start from 0.8. Okay, 0.8. Let us see. All right, it starts from 0.8 and converges in an exponential way to the reference, and you can play with all of the parameters of your system. This way you can go down. Actually, let me change this to 3 again. You can go down and put here that you have a legend. The first one is the velocity. Okay, black one is velocity reference. And the second one is velocity response, or you can simply write here it's reference versus response, ref and res, and you can write there that the x label is time, y label is velocity, so that's radian per second, right? Because we're talking about a rotational system. If you remember, we had the gravity effect over there. And the title as controller, oh well, let's say velocity controller responses. Okay, when you run this, everything will automatically come. You have the time, you have the velocity controller responses, which is showing you the reference and response. Likewise, you can copy this down for observation of disturbance torque. Disturbance torque was scope 06, right? Scope 06. And in legend, you should just have the torque. X label is time and Y label is disturbance. So it should be in Newton meters, right? And disturbance torque estimation results. When you run this, you're gonna have this one. Disturbance torque estimation result is something like that. Okay. If you play with those parameters, if you change A to be, for example, 12, let me see, probably you're gonna get different results. Okay, you can see that the result is now way different. The disturbance acting on the system is changing differently than the previous one, but still you have tracking performance. So in coded function, it's much easier to observe everything, and you can write all of these codes in Octave environment if you don't have a licensed MATLAB version. Well, having said this, I think it's time to stop because I already made a simulation. Maybe you can try at home to simulate a different algorithm, but be careful here. The plant side, the disturbance observer side, and the acquisition of the responses are more or less the same in any simulation you're gonna have. Just the parameters will change, like the parameters of the plant will change, or the required plotting, the required plots will be changing. But you have to pay attention to this acceleration desired. See, that's the tricky part. That actually combines, that actually shows what you're gonna try to focus on. If you have a position controller, you should change this acceleration desired to someone like kp times post-ref minus post-response plus kv times val-ref val-response plus acceleration response. Remember our previous derivations. Or if you have a bilateral system to be synchronized, so that you have to create the desired accelerations, you will have the desired acceleration for the first system and second system, and we have all derived these in our lecture notes, in our previous lecture notes. Well, I think that concludes my lectures. It was nice to be with all of you. I hope all of you are in good health, and all of you will stay in good health. In about a week of time, I will be assigning your project, which will take place of the weight of your midterm, and then for the finals, we will be waiting for the announcement of the school. Until then, take care, guys. Goodbye.